There are specific rules that we need to follow when we name our coordination compounds or our complexes. So this avoids ambiguity. Okay. Also, in the way we write the chemical formulas of our complexes or coordination compounds, there is also one rule that we must follow. But first, we will start with rules on how to name our coordination compounds. So far, we've only seen, so in the previous video, you've only seen chemical formulas, but they have names. So the first rule is the names of neutral coordination complexes are given without spaces. So the cation is named first and separated by a space from the anion, which is the case for all ionic compounds. So what does this mean, class? If you have a complex, like what you saw in the previous video, if you have a complex like this one in your compound, then the name of this complex is written without any spaces, as you can see here. Okay. If you have, for example, this one is one complex, and you see that there are no spaces in its name. So, yes, nakakahilo siya. But with practice, you will be able to name your coordination compounds in a breeze. Okay, just keep on practicing. Okay, so first, we see here, this is a compound composed of a cation, which is sodium, and an anion, which is a complex. So you have a cation and a complex anion. So just like how you name your ionic compounds, you start with your cation. So the name starts with sodium. Space, the name of your complex. So the name of the complex doesn't have any spaces in it. So dire-diretso lang siya. The same goes for this one. So you have your cation. So you name that potassium, space, the name of the complex. And then this one, this entire thing is a complex, a neutral complex to be more specific. So you don't see, no, this is also an ionic compound. So you have the anion there, and the cation is a complex. So you have the name of the complex cation and then the anion. So there's a space separating the two. And then the last example here is a neutral complex. So this neutral complex, in its name, you don't see any spaces. Dire-diretso lang siya. Okay. That's the first rule. So how do you name? You start with the cation and then the anion. If the cation is a complex, then you write the name of the complex, space, the anion. Okay. Rule number 2. The name of the coordination compound, whether it's neutral, cationic, or anionic, begins with the names of the ligands. And then the metal is listed next, following in parentheses the oxidation state of the metal. So, for example, here we see, so sodium, that's a cation. So you just write there sodium space, the name of the complex anion. Okay. So you start with the name of the ligands. So what are the ligands of this complex? You have chloride and ammonia. Okay. So this one should be alphabetical, following the name of the ligand. So in the previous video, you saw in the table that your ligands have names if they are ligands in a complex. It's not just their typical name as a molecule, but they have a special name as ligands. So for example, ammonia, its name as a ligand is amine with a double M. Well, ammonia has double M, right? So it's amine. And the chloride as a ligand is named chloro. Okay, so the order now, you start with amine and followed by chloro because it should be alphabetical. Alphabetical based on the name of the ligand. In the chemical formula, chloride comes first, followed by ammonia. That's because we have a different rule in writing chemical formulas. But in writing the name, you start alphabetically. Okay, so it's alphabetical based on the name of the ligand. Okay, so in the second example, we only have one ligand, which is bromine. So in the name of this complex, you see there bromo. In the second example, the cation. So the cation is the complex. So what are the ligands that we see here? We have ethylene diamine, iodide, and water. So water, its name is aqua as a ligand. Then this is followed by ethylene diamine. So there you see ethylene diamine. And iodide, its name as a ligand is iodo. Okay. And then in the second example, we have a neutral complex. So the ligands are this abbreviation PPH3, which refers to triphenylphosphine. So that's the name of the ligand. And then chloride ion. So you should see there chloro. Okay, so we are slowly building on the rules, and slowly we will understand how these names came to be. Okay, next, third rule. When more than one of a given ligand is bound to the same metal center or ion, the number of such ligands is designated by prefixes. So you have di for 2, tri for 3, tetra for 4, penta, hexa, hepta, octa, nona, deca, undeca, and dodeca. That is why in the name of our first example, what you see there is amine, just amine, because you have one ammonia ligand, trichloro. Okay, we end there. Trichloro. So the name there, tri, or in the name you see tri, that means you have 3 chloride ions or 3 chloride ligands in the complex. Here, in the second example, you see there tetrabromo. That means you have 4 bromide ligands. Here, you see, you don't see these prefixes, right? So you have aqua because you only have one water. You have iodo without any prefix because you only have one iodide ligand. Now, this bis will be tackled in a short while. Okay, let's be patient. Next, for the fourth example, you see there trichloro because there are 3 chloride ligands. Okay. Now, when it comes to your ligand, okay, if the name of the ligand already contains these prefixes, then you will use this instead to designate their number. So bis for 2, tris for 3, tetrakis, pentakis, hexakis, heptakis, octakis, and enea for 9. Okay. This is in the case of our polydentate ligands. In this example, we have ethylene diamine, which already contains the prefix di. So to tell us that there are 2 ethylene diamine ligands in this complex, we use the prefix bis enclosing the name of the ligand in parentheses. Okay, bis ethylene diamine iodo-cobalt 3 nitrate. Okay. In the fourth example here, we use here tris because you have 3 of this ligand. The ligand's name has tri. So we use tris to say that there are 3 triphenylphosphine ligands in this complex. Okay. Next. Neutral ligands. So if you recall, class, when we discussed ligands, specifically the monodentate ligands in the table, you have their neutral and anions. Okay, so this tackles neutral ligands. So neutral ligands are given the same name as the uncoordinated molecule, but with spaces omitted. So these are molecules that do not have special ligand name. Okay? Unlike water, 'di ba? Aqua, yung name niya as a ligand. Ammonia, its name as a ligand is amine, right? So these neutral ligands, you retain their name kung ano man yung pangalan nila as free molecules, but you don't have spaces. Okay, so you have the spaces omitted. So for example, so we've already seen pyridine, right? So pyridine, kung yung name niya as a ligand is still pyridine, and so on. So these are some examples: dimethyl sulfoxide, urea, pyridine, terpyridine, 2,2' bipyridine, ethylene diamine, we've already seen this, trichlorophosphine, and triphenylphosphine. Okay? Next, exceptions. So again, some neutral molecules have special ligand names. So I've mentioned ammonia and water. Others include your nitrogen monoxide. So its ligand name is nitrosyl. Carbon monoxide, it's carbonyl. And carbon sulfide, it's thiocarbonyl. Okay, or this is a carbon monosulfide, thiocarbonyl. Okay, rule number 5. Anionic ligands are given names. So we are now tackling anions as ligands. They are given names that end in the letter O. Okay, so for example, if the name of the free uncoordinated anion ends in 8, the ligand name is changed to end in ato. So we've seen, for example, acetate, its ligand name is acetato, sulfate is sulfato, carbonate, carbonato. And this one is an abbreviation. So this is acetyl acetate. Its name as a ligand is acetyl acetonato. Okay. If the name of the free uncoordinated anion ends in "ide", then the ending is changed to "ido". For example, nitride, which is nitrogen with a charge of -3, its ligand name is nitrido. Azide, which is N3 with a charge of -1, its ligand name is azido. Amide, amido. And dimethylamide, dimethylamide. If your anion's name ends in ITE or "ite", then you change the ending to "ito", such as nitrito for nitrite, sulfito for sulfite, chlorito for chlorite. Okay? And then you have anionic ligands with special names, but they still end in O, such as cyano for cyanide. So it's not cyanido, it's just cyano. Fluoride, it's not fluorido, but it's fluoro. And the same for your halogens. Oxide is not oxido, but oxo. This is superoxide. So two oxygens bonded with a negative charge. Superoxide. This is called superoxide, but its ligand name is superoxo, not superoxido. Hydroxide, not hydroxido, but hydroxo. Hydride is hydrido, and methoxide, methoxo. So these lists are not encompassing, but I'll probably send a more complete list tomorrow. Okay, let's go to rule number 6. So again, I already mentioned this. The ligands are named first, followed by the name of the metal. So what is the order of your ligands in the name of your complex or coordination compound? Alphabetical. But you ignore the prefixes. So going back to our examples, again, in the first example, the ligands are chloro and amine. So you start with amine, followed by chloro, and again, you disregard the prefix, indicating the number of the ligand. Here, there's no problem because you only have one ligand. Here, you have 3 ligands: ethylene, diamine, iodo, and water. So the first ligand to appear in the name should be aqua for water, followed by ethylene diamine, again disregarding bis, and then last is iodo. Here we have two ligands. So we have the triphenylphosphine and chloro. Okay, so chloro comes first, followed by triphenylphosphine. Now here, the tri is part of the name of your ligand. So you don't disregard it. Okay? You don't disregard it. So triphenylphosphine, its first letter is T, not P. Okay? Next rule. Okay. Now we go to the naming of the metal. So we are finished with the naming of the ligands in your complex. How is the metal named? So it depends on whether your complex is an anion, a cation, or neutral. So when your complex or coordination compound is neutral or cationic, the usual name of the metal is used, followed in parentheses by the oxidation state of the metal. So for example, we have this third example, the cation is a complex, right? So you see here, the name of the metal is simply cobalt, followed by its oxidation state. And the fourth example here, you have a neutral complex, so you simply write ruthenium, followed by its oxidation state. However, if your complex or coordination entity or compound is an anion, then the name of the metal, its ending, is transformed into 8. Okay? So for example, instead of platinum, here in our first example, the anion is a complex. So you don't write platinum, but you write platinate, followed by the oxidation state. In the second example, the anion is also a complex, but you don't write you don't write copper, you write cuprate, followed by the oxidation state. So you see the difference. So you have to be able to distinguish if in the compound, is it the cation, the complex, or the cation is a complex, or the anion is a complex, or do I have a neutral complex? Or is it the case that both cation and anions are complexes? Okay, if it's a neutral complex or a cationic complex, you retain the name of the metal, followed by the oxidation state. If it's an anionic complex, you change the ending, the name of the metal, the ending part of the name of the metal to ATE. Okay, so for example, here we see some metals whose names end in ium and how their names are transformed to the 8 ending. So scandium, scandate, titanium, titanate, chromium, chromate, zirconium, zirconate, niobium, niobate, ruthenium, ruthenate, palladium, palladate, rhenium, rhenate. But some other metals, especially those that do not end in ium, you still transform their ending to 8. So manganese, manganate, cobalt, cobaltate, nickel, nickelate, tantalum, tantalate, tungsten, tungstate, platinum, platinate. While for some metals, their old Latin names are used. So for iron, we don't say ironate, but we say ferrate. For copper, we don't say copperate, but we say cuprate. For silver, we don't say silverate, but we say argentate. And for gold, we don't say goldate, but we say orate. So the original Latin name of the metal is used as basis, and that's the one whose ending is transformed to 8. Okay? And then, so these rules from 1 to 7, these are the rules that you apply in writing the names of your coordination compounds. Now, how do we write the chemical formulas of your coordination compounds? So Just what you only need to keep in mind is that the metal center or the metal ion should always come first. And then the order of the ligands would be anions first, and then neutral ligands last. And then the order would be alphabetical. Okay, alphabetical order according to the first chemical symbols of their formulas. Which means if you have this tetraamine chloronitrito N cobalt 3 ion, your center is cobalt. What ligands do you have? You have amine. So this is a typo. That should be double M. Amine, chloride. You have 4 amine, 1 chloride, and 1 NO2. And then the charged ligands are chloride and NO2 or nitrite. Ammonia is neutral. So chloride and nitrite should come first. And of the two, it should be chloride because Cl, C, is first, or alphabetical wise, C comes first than N. So you're right, Cl followed by NO2, again enclosed in parentheses because this is one ligand, followed by 4 ammonia molecules. And then you should be able to derive the charge of your complex. Okay, so I leave it to you why the charge of this complex is +1. So the charge of your metal center is given in the name. You know that chloride has a charge of -1. Nitrite has a charge of -1 as well. Okay, ammonia is neutral. Okay, so those are the rules that we must follow in naming our coordination compounds or in writing the names or the chemical formulas of our coordination compounds. So now let's try to answer this very simple problem. What is the name of this complex? So first, again, we've identified cobalt. Cobalt is the metal center. The ligands, we have chloride, and we also have ammonia. 3 chloride, 3 ammonia. The whole complex is neutral. There's no net charge. So from the ligands, we have a net charge of -3 because ammonia is neutral. That makes our cobalt's oxidation state be +3, right? Okay. Next, ligand names. So we have chloro, and we have amine for ammonia. So 3, that's triamine, trichloro, cobalt 3 with no spaces. So it's not cobaltate because this is not an anion, okay? Because it's neutral. So the name is triamine trichlorocobalt 3. Next, what is the name of this complex? Okay, so here you must be able to recognize that this is an ionic compound, okay? You have the cation and the anion is a complex. Okay, the subscript of our cation is 3. Therefore, the charge of our complex is -3. Meanwhile, the charge of our cation is +1. Okay. Now, looking at our complex, the metal center is iron, and we have 6 cyanide ligands. So this is cyano. The name is cyano. From the ligands, we have a charge of -6. If the charge of the whole complex is -3, that means the charge of iron is +3. So what's the name of this compound? So this is ionic. So you start with the cation, which is simply potassium. Then the name of your complex anion. So that would be hexacyano. Now this is an anion. So the ending of our metal name is 8, hexacyanoferrate 3. Okay? Potassium hexacyanoferrate 3. Next, what is the formula of the complex dichlorobis ethylene diamine cobalt 3? Okay. So from the name, what can we deduce? There are 2 chloride ions or ligands. So that gives a charge of -2. There are also 2 ethylene diamine ligands. Ethylene diamine ligands are neutral. And then we have cobalt 3. So that gives a charge of +3. So what is the net charge of our complex? Should be +1, right? Now let's write the symbol for our metal center. That's cobalt. And then the rule again is you start with charged ligands. So we have Cl2 followed by the neutral, which is ethylene diamine with a subscript of 2. And then the overall charge of the complex is +1. There you go. COCl2 quantity N for ethylene diamine 2 and then a charge of +1. You can also opt to write the whole chemical formula of your ethylene diamine, but this one is more convenient, the abbreviation. Okay. Next, what is the name of the complex here? Okay. So let's list the ligands. So we have there 1 bromide ligand. So that's a charge of -1. 1 chloride ligand. That's a charge of -1. 1 methylamine. That is neutral. And 1 ammonia, which is also neutral. Okay, so let's write the ligand names. So that's bromo, chloro, methylamine, and amine for ammonia. Okay, the whole complex is neutral. From the ligands, we have a total charge of -2. And for the complex to be neutral, then your platinum center should have a charge of +2. So what is the name? That would be all of the ligands. We only have one of each ligand. So that would be, we start with amine. So that's amine bromochloro. Methylamine. Again, without spaces. Methylamine platinum 2. So the complex is neutral, so we retain the name of the metal. Is that correct? Yes. Amine bromochloromethylamine platinum 2. Okay. What is the formula of the complex hexaamine chromium 3 hexafluorocobaltate 3? Okay. If you are getting the hang of it, you must be able to recognize that the cation, which comes first in the name, is a complex, and the anion is also a complex. So let's start with the cation. So you have chromium 3 as the center, and you have amine there, so that's ammonia, and you have 6. Okay, ammonia is neutral. That makes your cation. Your cation has a charge of +3. So how do we write it? That's chromium. So that's CrNH3 6 quantity 3 plus. Then for the anion, you have cobaltate 3. So that's cobalt with a +3 charge. You have 6 fluoride ligands. That means you have a charge of -6, which means the charge of your anion is -3. So you have cobalt, COF6, 3 minus. Now, combining the two, the way you combine your cations and anions to form your ionic compounds, crisscross. So what we have is CrNH3 6 subscript 3 followed by cobalt COF6 subscript 3. But since they have the same subscripts, you just delete the subscripts because the subscripts are equal. Okay, so the final answer is this one. Okay. Do I still have an example? Yes. Okay, I have 2 more examples. What is the formula of the complex diamine tetrabromo platinum 4 bromide? Bromide. There shouldn't be a space there. Wala dapat space dyan. Okay. So, we have platinum. So, the metal center is platinum and oh, it's 6. I think that's a typo. It should be 4. That should be 4. Or is it 6? Let's see. I have the answer in the next slide. So let's stick with the given, which is 6. Okay, that's platinum 6. And we have 2 ammonia. And then 4 bromide, which gives us a -4 charge from the ligands. So that's +6 plus 4. The net charge of our complex cation is +2. So we have platinum followed by PTBr4, quantity NH3, 2, and then +2. Then bromide is the anion of the compound. So crisscross, so we have PTBr4, NH3, 2, Br2. Oh, okay. That's correct. So PTBr4, NH3, 2, Br2. Okay, so this is not a typo. Platinum 6 siya. Okay, next. What is the name of the complex? K2ZnOH4. It's very easy. Okay, so yung anion naman natin yung complex. So let's start with the anion. So we have zinc there. And we have 4 hydroxides. That gives us a charge of -4 from the ligands. By the crisscross method, the charge of our anion is -2, which means, okay, zinc has a charge of +2. Okay, so what's the name? It's potassium tetra hydroxo zincate 2. It's an anion, right? The complex is an anion, so the ending should be in ATE. So there you have it, potassium tetrahydroxozincate 2. Okay. Okay, this is the last example. So what is the name of this complex? So this is our cation. The anion is a complex. By the crisscross method, the charge of the anion complex is -2. The center is nickel. We have their oxalate. So we have 2 oxalate ligands. That's oxalato, right? The name oxalato. 2 times -2, that gives us a charge of -4 from the 2 oxalate ligands. And we have 2 water. The ligand name is aqua. The net charge should be -2. So nickel should have a +2 charge. So what's the name of our complex? That is ammonium, ammonium, sorry. ammonium diaqua, dioxalato, nickelate 2. Okay, let's check. Ammonium. Okay, why is it bis oxalato? It should be dioxalato. Okay, because you don't have any prefix in oxalatos, it should be di. Okay, this is okay. Let's use this. So it should be dioxalato nickelate 2. Okay, dioxalato nickelate 2. But I have to confirm that rule because there are some references wherein they use the prefixes bis, tris, tetrakis, etc. for polydentate ligands. So I have to confirm that. But in the reference that I used, they specified that bis, tris, tetrakis, and so on will be used only if you have di, tri, tetra, etc. in the name of your ligand. Okay. So for here, I use that rule. That's why I have diaqua dioxalato nickelate 2. But I will confirm that class for clarity. Okay. So this ends the video on naming coordination compounds. So in the next video, we will talk about isomerism. Okay, so if you are not familiar with isomerism, we will define it first before we dive into this phenomenon in coordination compounds.